Differential equations, differential linear equations, are of the form dy dx plus p of x y equals f of x. P of x and f of x are functions of x, and this is what is called standard form of the linear differential equations. Now, differential equations that are linear involve what is called an integrating factor. And the way we go about solving these types of differential equations is first by expressing the differential equation in standard form, which is in this form dy dx plus p of xy equals f of x. We then need to find the integrating factor. Once we've found the integrating factor, we're going to multiply each of these terms of the differential equation by that integrating factor. And the reason we do this is we get a situation where the left-hand side reduces to the derivative of a product of variables by using the chain rule. And that is the reason why we establish an integrating factor and multiply every term by that integrating factor, is to then reduce the left-hand side to a quantity that can be integrated. So we're just going to show where we get that integrating factor from. So we'll just call this integrating factor I of x. You'll see it expressed differently in several textbooks. This integrating factor, so the situation that I'm referring to that we're going to get to is d dx, right, of this integrating factor times y. So we're looking for the product of the integrating factor and the variable y, the variable that you can see here, y. And we want a situation where the left-hand side reduces to this. And the reason we're looking for that, if we use the chain rule to differentiate this function, we're differentiating with respect to x. So we're going to differentiate the integrating factor, which is a function of x, and we're going to differentiate y with respect to x as well. So using the chain rule, this equals the function, the integrating factor, is a function of x. So the derivative is simply going to be I prime x, or if you prefer, it's d ix dx. So using the chain rule, we differentiate I of x. So we have I prime of x times y, plus, using the product rule here, I of x is now the constant, and we're differentiating y. So the constant of y, we're differentiating y with respect to x. The constant is now I of x, so the derivative of that will just be I of x, and then we have dy dx. Okay, if we multiply the left hand, every term, by this integrating factor, we will have I of x dy dx plus p of x I of x y, and that equals f of x times I of x. We're not going to look at the right hand side for now. We're simply purely going to be looking at the left hand side and compare it to this over here. So we can clearly see that we have I of x dy dx over here. Now for these, because we're looking at the left hand side here, these have to be identical. So we have this part I of x dy dx present. Therefore, we can say that y I prime of x must equal p of x I of x y. Okay, the y's will cancel. So in other words, we have I prime x equals p of x I of x. This is variable separable now, so we're just going to divide both sides by I of x. And now we're going to integrate both sides with respect to x. So this equals the integral of 1 over I of x, and we have dix dx, and that equals the integral of p of x dx. So when we integrate this, 1 over I of x with respect to x is going to give us ln I of x equals the integral of p of x dx. We don't know what p of x is. It's a function of x, and hence we cannot express this in any other way, right? We can now solve for I of x, so we can raise both sides to the power of e, so it'll be e to the integral of p of x d of x, and this is the integrating factor. This is the formula for the integrating factor. So once we've established what p of x is, we're then going to use this formula e to the integral of p of x dx to then establish the integrating factor. Once we have the integrating factor, we multiply every single term of the differential equation by that integrating factor and then reduce the left-hand side to a form that can be easily integrated. Okay, so question 1. This is already in standard form. Just to recap, standard form is dy dx plus p of x y equals f of x. So p of x we can clearly see is the coefficient of y here. So p of x equals 1 and f of x is this over here, e to the 3x. So the integrating factor I of x equals e to the integral of p of x dx. So that's e to the integral of 1, p of x is 1, dx. Integrating 1 with respect to x just gives us x. So the integrating factor is e of x. We're not too concerned about the constant here. Whenever you integrate, there's always an integration constant. We're not too concerned about that here because we're looking at a family of solutions with regard to the differential equation, not looking for a particular solution. So it really doesn't matter. The derivative of a constant is always going to be 0. So it actually doesn't really matter at this point. We're now going to multiply every term of the differential equation by this integrating factor. So we will have e to the x dy dx plus e to the xy equals e to the 3x times e to the x. The left-hand side now is going to reduce to this form, d dx of e to the x times y, and that equals e to the 4x. We're multiplying powers with equal bases, we add the exponents. Now before we solve this, we're just going to show that this d dx of e of x times y will give us that over there. So we're differentiating with respect to x, e to the x times y. So because we're differentiating with respect to x, let's start with a function that has an x. The derivative of e to the x with respect to x, the derivative of the exponential function is the exponential function again. And using the chain rule, we have to multiply by the derivative of x. And the derivative of x is just 1, so we're not going to put that 1 in. We don't need to. And y with respect to x, because we differentiate with respect to x, y is constant, so we have the y. And using the product rule, we now also have to differentiate with respect to y. So e to the x now is the constant, so we have e to the x. And the derivative of y is 1, but there's only a y here, right? So there's no x variable present here, so the derivative is 1. We'll just put the 1 in for now, and then we have to have dy dx. The reason we have this is because there's no x present as part of that y over there. So this is e to the x times y plus e to the x dy dx. And you can clearly see this is what we have over here. We have e to the xy, which is that term there, and e to the x dy dx, which is that term. Okay, we can now integrate both sides. So we're going to integrate both sides here. The integral of d dx e to the x times y is just going to be e to the x times y. And the integral of the exponential function is the exponential function again, but we divide by the derivative of x. The derivative of x is 4, so we divide by 4, and now we have our integration constant c. We can call that c1. So, as we are solving for y now, we're going to divide every term by e to the x. So we have a quarter e to the 4x times e to the minus x plus c1 e to the minus x. And that equals y equals a quarter e to the 3x plus c1 e to the minus x. And if you prefer, we can just call that c1 a constant. We could have just left it as c. It really doesn't make a difference if you use a subscript or not. It really makes no difference. So this is a solution to the differential equation.